Good morning, I'm Paul Baker. I'm a building physics consultant and I've just recently retired from Glasgow Caledonian University. I'm going to give an introduction this morning to the LORD software and mainly to go through how to use the software, and I'll give some examples of how to apply LORD to data. For example, the PSA data that Maria has just presented. I'll also look at data processing for input into LORD, and that also includes estimating results by steady state methods to give a comparison with identified values from the software. Hopefully, the presentation will show you that LORD can enable you to quickly develop models for data analysis to derive the thermal characteristics of components or buildings. LORD was developed in a series of European projects by Olaf Gutschke of BTU Cottbus University to analyze dynamic test cell data, very much like the PSA test cell, but on a slightly larger scale, with the objective of delivering high quality performance characteristics for building components tested in real climates. So there were test cells from Finland right down to CMAT in Spain, so quite a wide range of climates. So LORD can be used for components, walls, windows, whole rooms, or more complicated systems, essentially to obtain thermal transmittance values, solar gains, and dynamic information, for example, capacitances and time constants. A transient mathematical model is assumed, and the parameters of the model, e.g. resistances, capacitance, and heat flow admittances are used, which define the dynamic and steady state thermal and solar properties of the system. The user essentially defines an RC network. Initial guesses of the parameter values are made. Often these can just be sort of default values. The output of the actual test, for instance, the test room temperature as a function of time, is compared with the output which the model produces for the same input conditions. By statistical analysis of the deviations between the model and the measured outputs, the parameter values are progressively adjusted in order to prove the agreement. I suggest you read the LORD manual and the other documents which will be provided. I'll go step by step through process of using LORD. So initially, you go to the input data tab and open a relevant data file. In this case, for example, series 16 from the PSA data. And then you can transfer that data into the project. You can either select particular variables, or you can transfer all of the data into the project. The file formats used are either tab delimited or comma separated variables. And it can be a bit tricky. You've got to ensure that the headers are enclosed in single quotation marks, so that the program actually identifies the column variable name. The second step is to create a model. You have on the right, you can add conductances to the model, and you can either fix these or make them variables for identification. Similarly, you then get the capacitances, and it's usual to set the capacitances at the internal and external nodes to 0, and the other capacitances are usually fixed at 0. There's a default time step of 60 minutes, but for example, you may want to use 10-minute data, so check that you've got the right time step. So now we have a basic, I'll just return to the, hold on. So in the output section, sorry about this, something's not appeared on the presentation. In the output section, you need to specify one or more variable, usually one, for example, heat flux or the internal temperature. So we now have a basic 4-node model, which could be applied to heat flow measurements through a wall, for example. Then we go to the link data to nodes tab, and there we define which variables are applicable to each node. Usually in a simple model like this, you will have the external temperature on node 1 and the internal temperature and the heat flux on node 4 in this case. We go back to the model tab, and the aperture, which is the heat flux, will appear, and it's normal to set this to 1 and fix it. And similarly, if you have heating power in a room, you would also set that to 1. But if you have solar radiation, for example, in the model, you usually use that as a variable aperture, and the LORD program identifies the relevant coefficient to apply to the solar radiation to get the solar aperture of the system. Here we are. So we now select the output, and for example, in this case, I've selected the heat flux. The next step is to define where the U and G values are applied. So usually we define the interior and exterior nodes. So for this model, we identified the interior node as node number 4, where the heat flux is applied, and the exterior node as node number 1. In this case, we have no radiation, so that's not specified. You can set the initial startup conditions for the model to be applied to the nodes within the model. So you've got 3 different options. You can identify them like variable parameters, or you can set them as a constant temperature, or in certain cases you can also let them constant at their actual values, which would be the case if I'll explain later on if you use the program in simulation mode. Usually I would use identify like variable parameters. You can also set limits for the parameters. So this is the sort of range of conductances, capacitances, and temperatures that you would expect from the model. But initially, it's perhaps a good idea just to not set the limits and see how the model actually runs, and then apply limits if you feel that would, particularly with things like the capacitances, sometimes they go a bit haywire, and it's better to apply some restraints on the values that are generated. You can use 2 methods for identifying the parameters. There's the output error method and the prediction error method. LORD was originally developed using the output error method, and the prediction error method was added later. The residuals are usually smaller if you're using PEM than using the output error method, but the identification process takes much longer using PEM, and you're restricted to using temperatures, and you can't use it with, for example, heat fluxes. Ask a statistician to explain the differences. But I recommend that you stick with the output error method, because you can quickly run a model and then perhaps if you accept that you've got a satisfactory model, then you can perhaps then use the prediction error method. There are other options in LORD. For example, you can use create functions which, for example, you can use to create a variable resistance which could be dependent on a measured parameter such as wind speed. I've tried this in the case of an old building with a very high air change rate, and it did to some degree help to improve the results, but it's probably not something that you would normally use. But I can see, for example, if you were concerned that say the thermal conductivity of one of the materials was dependent on temperature, then it might be useful. There are other options in terms of the output graphics, and you can apply fitting windows to the data. So you can select a particular part of the series to for identification. LORD gives instructions for this, which it's easier to follow when you're actually using LORD yourselves. You can also create, for example, a daily pattern of data. This could be useful, for example, for excluding daytime data for heat flow measurements through glazing, where really you want nighttime data with no solar radiation to make a good estimate of the actual U value of the glazing. So then you are now ready to run the program, and it will automatically stop when it's satisfied that you've got a good statistical agreement. The output files, you have a log file which gives all the input and output information concerning the model. And you have a res file which gives the measured and calculated values of the output variables. So you can use that for further statistical analysis and for comparing for example, identifying the residuals and doing statistical checks. The final option, you can run an error propagation routine. So, for example, if you know the errors on the different input variables, the external, internal temperature and the heat flows, then you can estimate the uncertainty of your value. You can use LORD for simulation or validation. For example, you could validate the results from one part of a data series on to another part. So identify a model for series 16 from the PSA dataset and apply to series 18. So firstly, you just run LORD for series 16 only, and then obtain results and save the model. Then you fix all the parameters in a new calculation for series 18 using the model for series 16. So in the model tab, you basically fix all the variable conductances, capacitances, and apertures. Then you set the initial conditions to third option, let at their actual values. So move the window in the output graphics over to series 18 and then run LORD. If you've correctly fixed everything that you need to fix, you'll just get a message which says there are no variable parameters, therefore the calculation was done in simulation mode. So only one run is performed. Here we can see the results. So the yellow window contains series 18, and from the residuals, it looks like the model for series 16 works well on series 18. So that gives us confidence in the model. Series 17 in the middle there are a few higher residuals. Now, the capacitance values that LORD gives are really like a mathematical fix. So to actually obtain time constants and capacitances from the LORD output, what you need to do is to run LORD with a data set, for example. In this case, it's an older test data set. Save the model when you're satisfied with the results, and then go create a simulated data file. So you could use the heat flux from the original file, which is not used in the next step using LORD in simulation mode. You create a fixed external temperature and a fixed internal temperature with a 1 degree step change. So the actual data series looks like that for the two temperatures with step change in the internal temperature. So open the simulated data file in LORD, load the model previously used. Again, fix the parameters in the model, fix the initial conditions, set the output to heat flux, run LORD, and it should run in simulation mode. Open the res file, which gives the measured and calculated values of the heat flux and find the period corresponding to the step change. So here we see the output from Lord, the calculated values. Ignore the measured values completely, and you can see that we have a spike in the heat flux at the beginning of the step change, and we from graphically or from the data that you've got in the Excel file, calculate the time from the start of the step change to the final value of the heat flow when it reaches a steady state. So from that graph, we've identified that the time from the start of the step change to the steady state condition is 47 hours. Now we can choose the time constant tau or 3 tau to calculate the time constant. So we multiply the time t by 63.2% for tau, which gives a time constant of about 30 hours. And 3 tau is 95% of t, which is about 45 hours. We know that the resistance of the model is a value of 2.54, and the capacitance is the time constant divided by the resistance. So for just using tau, it's 11.7 watt-hours per k meter squared, and for 3 tau, it's 17.6. So that's one method using Lord of doing this calculation, but perhaps you'll find out from other presentations that there are other methods using different software. So now application of Lord to real data. Firstly, the data must be processed for input in Lord. So you need to check the integrity of the data. So plot the data in Excel or other software. Check for any missing data, any anomalies. Then Maria's talked about the effect of using different averaging periods. So, you know, what period do we need to use for example the PSA series data? So the data are provided at 1 minute intervals. So is that too much information, or will it involve too long computation times? If we take the roll sequence in series 16, it's based on 30-minute periods. So the maximum interval to include all dynamic information from the roll sequence is 30 minutes. It could be better to use 10-minute averages rather than the 1-minute data. First of all, you need to identify where the start of the roll sequence is. In this case, we would start averaging at the beginning of series 16 at 1300 hours. On the, sorry, no, that's wrong. It would be at the beginning of the data file at on the 6th of December 2013. And this would capture all the dynamic information. So the following figures show the effect of different averaging periods on the actual data. So at the top left, we have the heating power for 10-minute data, and at the top right, we have the heating power at 30-minute intervals, and you can see that generally speaking, there's quite good agreement. The 30-minute averaging period does have some smoothing effect. Then if you use 1 hour, you can start to see that there's quite a difference between the hourly average and the 10-minute average. And obviously with daily averaging, as you might do in a steady state analysis, then you really lose the dynamic information. Similarly with the solar radiation, you can see that it's not so bad with the hourly data, but again with daily data there's an obvious disconnect with the original dynamic information. External and internal temperatures may be, again, the worst case scenario is using daily data, which may or may not be useful for a steady state type analysis. Again, with surface temperatures. Heat flux, you can see that there's quite high spikes in the heat flux data in the 10-minute data when at the start of the roll sequence. And if you use the 30-minute or the 1 hour data, you tend to smooth this out. But with the daily averaging, you basically lose all the dynamic information. When we look at the heat flux measurement data from PSA, it's perhaps useful to estimate results initially by a simple averaging method before running load on the data. I've tried 3 approaches using the different temperatures available, and these give a good idea of the U-value results you should expect to be aiming for by identification. You may, in fact, improve on them. Using LORD, here we're using the rear wall as an example, and I've used the basic 4-node model. I've used the external surface temperature, TSE, and the PT internal temperature, TSI, because this one is more local to the heat flux sensor. I've also tried TSI average, which is made up from a number of sensors locating on the rear wall, and also the internal room temperature, DI. But I found that TSI temperature near to the heat flux meter produces better results with lower residuals. As you can see from here, the top left is the single measurement near the heat flux meter. Top right is the averaged temperature, surface temperature at the back wall, and the residuals you can see are higher. And similarly, if you use the internal air temperature for the output. So TSI appears to give the best fit. Here we have calculated and measured data using different periods for the averaging of the data. So the top left is using 10-minute data. The top right uses 30-minute data, and the bottom left uses hourly data. So these are for series 17, and you can see actually that you get the same results for the different averaging periods, and also for the whole steady state averaging method, which is good. Here are the residuals. Can actually see that, for example, using hourly data improves the residuals, as it tends to smooth out more extreme spikes, but it could be that you also need to improve the model. For example, here we used the temperature as the output variable, but you could try using heat flux. Now we look at UA and G values for whole test cell data in the co-heating test of a building. If we look at the heat flux measurements on the walls, then we can easily get an idea of the U value by the averaging method. But this is not possible for UA and G values. For steady state conditions, the electrical heat input to maintain a constant internal temperature within the test cell or building will increase when the outside temperature falls, and decrease when solar radiation rises. In reality, these are always fluctuating, but they're dampened by the thermal inertia of the room. However, you can't measure the heat loss coefficient or the solar gain directly. But we can start off perhaps with a steady state Siviour analysis for the data series. And this is something that is applied, for example, for co-heating tests of real buildings where a constant set point is applied within a building, and you collect about 2 weeks data, and you measure the internal, external temperatures, the heating power, and the solar radiation. And this form of analysis, you take daily averages or longer, and the heating power is equal to the UA value times temperature difference minus the solar aperture times the global vertical radiation. And if we divide this through by the temperature difference, we can plot on a simple XY plot the heating power divided by the delta T against the solar radiation divided by the delta T. And the intercept on the y-axis is the UA value, and the slope of the line is the solar gain factor. I mean, in this example, there's a reasonably good correlation. So I've applied this to the different parts of the data series 16 to 18. If we plot all the data, then, as you can see, there's not a particularly good correlation, but the actual U value, the intercept on the y-axis, we know that that is not a bad estimate. If we look at the individual series now, we can see that the steady state co-heating test data in series 17, where you've got a high temperature difference and regular solar radiation peaks, gives a good correlation, and compared to the other two series, where with series 16 you've got the Rolls sequence, and in series 18 you've got a relatively small temperature difference. So for the steady state, the best data is the one with the high temperature difference. It could suggest that this would possibly give results for steady state parameters using LORD. But we can create a 6-node model with LORD. It could be less, and we essentially have the heating power on the inside and the internal temperature. We have T external on the outside node 1, and we assume that there's 2 admittances for the solar radiation, one on the outside of the cell and one entering the cell. Now, if we look at series 17, you can get a good fit, but the model doesn't really fits the rest of the data. But now if we use series 16, we find that actually that's with the dynamic information, it gives you a better identification of the parameters, and you get a reasonable fit to the other data series. So I expected the series 17 would give good results. However, the UA and the GA values using series 17 in Lord are high, and the fit is poor to the rest of the data. So series 16 gives better results and overall better fit to all data. Do we use 10-minute or hourly data? Are there problems with high frequency data using Lord? Should we try a different model? These are questions that perhaps you can explore. So some comments and conclusions. So firstly, it's important to understand the physical system, for example, the construction of the PSA test cell and the sensor locations. Plot the data, check for integrity. Use simple averaging or the Siviour analysis to estimate results prior to using the identification techniques. Select suitable data averaging periods, particularly for the dynamic test sequence. Compare different parts of the test sequences. It's also possible to estimate time constants using simulation mode and capacitances. A useful reference which basically lays out the reasons for using identification techniques rather than steady state techniques is given here. All these presentations will be available. So first of all, thank you, Maria, for your presentation, and thank you all for attending today's webinar. Again, repeating Maria, you can send any further questions that you might have via email to Hans Bloom. And now I will close the webinar. Thank you very much. Goodbye.